Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
On May 1st, 2015, a group of scientists predicted that the following November, we should see a star that will go supernova billions of light years away in a spiral galaxy called SP1149.
This was the first time anyone had ever tried to predict a supernova. And that's for good reason. They are extremely rare and often unpredictable. For a star larger than 8 times the mass of our sun, a supernova is like the end of its life cycle.
So it's like the supernova is saying like, I'm running out of fuel. My core is almost empty. I can't hold on much longer.
And then the narrator of the story would say something like, the star, after millions of years burning brightly, has exhausted its fuel. It struggles to maintain its form as its core begins to collapse inward under its own gravity.
And like also, the collapse accelerates. And in a final, desperate moment, the star can no longer withstand the immense forces within.
And the star meanwhile is weakening and saying, I can't hold it. I'm exploding. And then in a brilliant cataclysmic burst of energy, the star detonates into a supernova, its light outshining entire galaxies. And in its death, it becomes a spectacle of unimaginable power.
And this is the star's final act. It will shine brighter than ever before, but only for a brief moment.
And as the light fades, the star's legacy remains, leaving behind a beautiful remnant, a bright supernova.
Now, a supernova can be as bright as a whole galaxy, right? As you just said.
Yeah, correct.
But more importantly, for our dear physicists like Edward Witten and all the light emitted follows a predictable pattern. It glows brightly for a few weeks and then reduces or fades down over a few months.
But supernovae are rare. In any galaxy of 100 billion stars or so, you can expect on average like only 2 per century. So like try picking the star that is going to explode. You can't. Like it's too hard.
Like on God, bro, bilkul sahi bola. Now, we can say how long a given star will live based on its mass, luminosity, and color temperature. These three factors, like together, they pinpoint the stage of life of a star as a predictable life cycle part, right? But the estimate of exactly when it'll go supernova, let's just say it has big error bars.
Yeah, just take the red supergiant Betelgeuse. Okay, I know I'm not
Betelgeuse.
Betelgeuse. Okay.
Yeah.
Yeah.
Butchering names again.
Yeah. It's a hobby. So, yeah, if you take that for example, yeah, that was in our own Milky Way galaxy. We think that it is a great candidate to go supernova, and scientists think that it'll explode anytime now in the next
Next
few.
days.
Nope.
Okay, months.
Closer.
Years. Couple of years.
Yeah, that's right. It's 100,000 years before it goes boom.
Oh, wow. Okay. But when it does, it'll be so bright that you'll see it in the daytime, and it'll even rival the full moon's dark like brightness in the night.
Now, we have to keep in mind how far Betelgeuse is compared to the moon. That is on literally orders of magnitude.
And still it like rivals the moon's
Yeah.
brightness. So 100,000 years is like for us short-lived humans is like means
Forever.
it'll be forever.
Yeah.
Right. But compared to the lifespan of a star, 100,000 years is like a brief window of their time, like of their lives, right? Because they can easily live for billions of years.
Correct. So you might think that it would have been a tough sell when the scientists who predicted we'd see a supernova in November 2015 asked for like some time on the Hubble Space Telescope to take pictures of the galaxy SP1149, like because of its large uncertainty.
Yeah. But surprisingly, this request was like granted. In the first image that the Hubble Space Telescope took, it was taken on October, there was no supernova. But in the next image that was taken on November 14th, scientists saw something.
What? What did they see?
A bright, starry night sky, but no supernova.
Bruh.
Now in the third image taken on December 11th, there was a supernova, right where they predicted it, and it was like almost exactly when they said that it would happen.
So how did they manage to predict a supernova almost to the month?
Well, the like truth is they had actually seen the same one like before, not once, not twice, but like 4 times.
Huh?
Like basically a year earlier, before the prediction, a year and 5 months before the prediction, the Hubble had already taken an image that had four bright dots. And those four bright dots were multiple images of the same supernova. So they've already seen it 4 times before.
Yeah, I think I know the reason behind this. The
Yeah.
reason we see the same supernova in four different locations is because there's a lens between us and the exploding star. Not a lens made of glass, of course, but something we like to call a gravitational lens. And it's made of a huge amount of ordinary matter and dark matter.
And dark matter is like, we'll talk about that in another episode.
Yeah. And this, what we term as gravitational lensing, tends to magnify distant sources and increase their apparent brightness as rays of light become more and more concentrated.
Yeah, that's why we can see the galaxies from far away, right?
Yeah.
So this gravitational lensing also smears the image of distant galaxies into arcs, strands, and all kinds of weird shapes. Like it increases their brightness, but it still like smears them out. So, so to some distant observer in another galaxy, the light from our sun and Milky Way might be warped for them,
Yeah.
like how the other stuff is warped for us.
Correct.
So in gravitational lensing, there are three essential components: the source, the lens, and the telescope. If the lens and the source are spherically symmetric, and if the source, lens, and telescope, all three are perfectly like in the straight line, perfectly aligned, then you get what's known. So basically, these two conditions meet, then you get what's known as an Einstein ring.
Ooh, fancy.
Yep.
So the light from the source is bent around the lens equally in all directions, leading to the image of a smeared out ring. If the source and the lens are spherically symmetric, but they're not perfectly aligned, what we end up seeing is a break in the Einstein ring. It splits into two semicircles. And if the source, lens, and telescope are aligned, but the lens is not axially symmetric for
Like basically
example,
not perfectly symmetric.
yeah, some like an elliptical shape, for
Yeah,
example.
fair.
Then you get four images in the shape of a cross, which is what we call an Einstein cross.
Nice. So what happened to a supernova is 9.3 billion years ago, a dying star in a galaxy far, far away went out with a bang as a supernova. And that explosion sent out a blast of light in all directions.
About 5 billion years ago, before the Earth even existed, that light encountered a very massive object that warped space-time. It was a cluster of galaxies called, okay, brace yourselves, MACS J1149.5 plus 2223.
Oh, also similarity. The galaxy was SP1149, right?
Yeah.
Yeah. So now we know that like all that what Pratham just said is a mouthful, but the name just tells us where in the sky it was found by the massive. So MACS, that's what you said. So massive cluster survey. So MACS. So that galaxy cluster is made up of lots of more massive substructures like individual galaxies and halos of dark matter. So like that's those points and all are just for the clarification of
Yeah.
the point.
And when at some point, as the light traveled through this region, it encountered an elliptical galaxy almost perfectly lined up with where the Earth would eventually be. The gravitational deflection focused light rays that were initially diverging onto paths that converged at the Earth. This is why we saw the same supernova in four different locations.
Yeah. Also, the supernova appeared at four different places because they were at different times also. Relative to the first image, the others were delayed by periods of like they were ranging from 5 days to over 3 weeks. And we can even measure this time delay because of the distinctive light curve of the supernova. And some of the images of the explosion were further along in the light curve than others, right? That's why the time delay occurred.
This was a particularly lucky discovery. The first time a multiply lensed supernova had ever been observed.
Yeah.
There are other objects that, due to gravitational lensing, appear multiple times on the sky, like multiple images of galaxies. But these objects don't change predictably with time, so there is no way to use their images to work out the relative time delay between them.
And one reason for this time delay is because the four paths were of different lengths, right? Because they're taking different.
Correct.
It's not like a straight line, each of them. So it took the light longer to travel further. Simple thing. And there's another reason that light passing through the curved spacetime appears to travel more slowly relative to an external observer.
General relativity. Tensor calculus, my dream.
Yes. This is much less intuitive, but it's it's a well-established and well-tested part of general relativity. Like, for example, back in 1964, Erwin Shapiro suggested that it will be possible to test this gravitational time delay by sending radar signals to Venus and measuring how long it takes for the echo, like so-called echo, to come back.
Yeah, he calculated that due to the gravitational influence of the sun, the signals took an extra 200 microseconds.
Oh, that's so significant, right?
Very, very significant. Very. So they took an extra 200 microseconds when like Venus was on the other side of the sun compared to when it was close to us and there was no interference of the sun in
Fair.
between. And this is solely a gravitational time delay and not related to the extra distance the light has to travel.
So, like, that's proof.
Yeah,
So, within a couple of years, this experimental data revealed that gravitational time delay for light traveling past the sun was exactly as predicted.
correct.
So today, in order to accurately determine the time, like the distance to the Voyager, like the craft or the Pioneer spacecrafts, this Shapiro time delay has to be taken and is always taken into account because, like, you have to, right? Otherwise, you'll get it orders of magnitude off.
Correct. It's very significant.
Yeah.
So scientists had been studying and modeling the distribution of matter in the cluster long, long before the supernova. They basically asked if we see these four images of the supernova in one image of its host galaxy, when would the supernova appear in these other two images of the host galaxy, right? Using the models of mass distribution and general relativity, they calculated that in this image, the supernova would have appeared exactly 20 years earlier in 1995.
Okay, but the thing is, we don't have close-up pictures of this part of the sky from 1995, right? So you can't really check, but that's what we expect.
Correct.
So, but in another image of the galaxy, they predicted that the supernova will appear again in about 1 year's time. At that time, right?
Yeah.
And that's when it showed up in November, like around when it showed up in that Hubble image, when it actually showed up, like properly.
Correct. So this successful prediction is a fantastic confirmation of our understanding of light and gravity in the scale of our whole universe, basically.
Yeah.
But somehow I feel like it has bigger implications because one of the hottest debates in astronomy right now is how fast is our universe actually expanding? Like, do we really know about it?
I mean, this question, it's almost like asking how light is a particle and a wave. But like, no one knows for sure, right? Like 100%. But there are some ways of knowing some stuff about it, like some ways of measurement. And the measurement of how fast a universe is actually expanding is measured by the Hubble constant, the rate at which distant galaxies are receding, depending on the distance between them. So there are two main ways that this has been traditionally made. One is to look for stars in the nearby universe whose absolute luminosity we already know.
Yeah.
Then we can use some equations we have learned in physics HL already
Yeah.
to see how bright they appear to us to determine how far they are. And if you combine this distance information with how redshifted the light is, you can work out how fast the universe is expanding.
By the way, redshift is basically an increase in the wavelength and corresponding decrease in the frequency and photon energy of electromagnetic radiation. So, this method of calculation is known as the distance ladder method, and the value of the Hubble constant that we obtain from it is like around 74 kilometers per second per megaparsec.
And a parsec is like a really big unit of distance. Like, and a megaparsec is obviously even bigger. Like,
Yeah.
But for every megaparsec that separates two different galaxies, we said, right, that depends on the distance apart.
Correct.
So every megaparsec that separates it, they will be moving on average 74 kilometers a second. That's like obscenely.
That's
like,
quite a lot.
yeah. But like, we need to keep in mind that the speed of light is way more still.
Yeah, and all the scale of the universe, this is like a tiny, tiny, tiny fraction of it. So.
Yeah, and we ourselves as humans have reached like I think 19 with one of the spacecrafts. Like it was obviously unmanned. I think 19 is the limit. We've reached up to now. So the other way to measure the Hubble constant, like without this, is to study the features of the cosmic wave background radiation, cosmic high energy cosmic rays we did earlier.
Yeah.
So it's essentially a picture of the early universe because light takes some time to travel, right? It's not infinite speed. So we spoke about it in our previous episode, right? So we called it a byproduct of the Big Bang.
Yeah, I remember. So, using this standard model of cosmology, which is called lambda CDM.
What's the full form of CDM?
I don't know.
Okay, go on.
We can work out how this early universe, like, it would expand over time. The result obtained from this method comes out to around like 67 kilometers per second per megaparsec, which is, when we think about it, substantially slower than the 74 which we found out like with the other method.
I mean, at least it's not orders of magnitude apart.
Yeah, but of course, whenever we try to quantify something that seems unquantifiable, this always happens.
Fair. And over the years, both of these techniques have been like refined, and we've reduced their techniques, like reduced their uncertainties, but the values still haven't like come closer together like as much as was right now. Like it's so this at this moment, these two values really seem different. Like they're not the same.
Yeah, and astrophysicist Joseph Silk, he called it a possible crisis for cosmology.
Oof, oof.
But there are independent ways with which we can measure the Hubble constant as well.
Okay.
And one of them is to look at a multiply lensed supernova and use the time delay between their appearances to work it out.
Oh, like what we just did, kind of like that only,
Yeah.
right? Yeah. So this was first proposed by a Norwegian astronomer, Sigurd Refsdal. That's definitely not how to pronounce it.
I think it's Thier, like Norwegian, the J
Oh,
is
yeah,
like
yeah.
Y.
Yeah, Sigurd Refsdal.
Great. Another name for us to butcher.
Yeah.
I heartily apologize to every scientist for mispronouncing their names.
Yes.
Sorry, gods of physics.
And this was in 1964. And the most ironic part of the statement was that most physicists are atheists. So gods of physics, so like,
Yeah.
what is God?
You know what? We should do an episode on this sometime later. Like, what
We-
is God? Shit, I'm so excited.
Arey bhai, please don't digress into philosophy. We'll do that. We'll brainstorm about all this antaryami stuff later, but focus on the stuff now.
Okay. Yeah.
Yeah.
So, since this is the first observed multiply lensed supernova, it has become known as supernova Refsdal, right?
Nice.
After him. Calculations of the Hubble constant from this data yield a value of 64 kilometers per second per megaparsec. And although the result has very large error bars, it is more in line with the measurements of the cosmic microwave background than with the distance ladder method.
That was like 74.
Yeah, and cosmic microwave was 67, so that's
Yeah.
closer.
So the thing that I keep thinking about is like space is stage. Yes.
Yeah, agreed.
I mean, I used to think of it as essentially like glass, fundamentally transparent stuff with some foggy regions or some slight distortions, right? Like,
That's damn metaphorical and quite deep. Like, you've been studying too much English recently. I think you need to tone it down and like come back to physics.
yeah, I wish. But we have here space that's warping light on different multiple curved trajectories that's making the same event happen in like 6 different places on the sky, separated by days, weeks, and years, and 20 years also.
Oof. And what is contained in these distortions is information about the workings of our entire universe.
We love hearing from our listeners and are always excited to dive into new topics.
You can reach out to us on quarktalkofficial@gmail.com at any time.